March 12, 1943, Hamilton Army Airfield, California. The morning sun cast long shadows across the concrete runway as Captain James Mitchell pulled his leather flight jacket tighter against the desert wind. Two identical North American P-51 Mustangs sat side by side on the tarmac, their polished aluminum skin gleaming like silver bullets ready for war. Same Packard Merlin engine, same .650 caliber machine guns, same pilot strapped into each cockpit. But only one of these fighters would return from today's mission over the Pacific. The other would run out of fuel somewhere over the endless blue expanse, its engine starving to death while enemy territory remained tantalizingly within sight, but impossibly out of reach. Mitchell had been flying combat missions for 8 months, watching helplessly as American pilots pushed their aircraft to the very edge of fuel capacity, only to turn back short of their targets because standard operating procedures demanded engine settings that consumed gasoline like a thirsty beast. Every bomber escort mission became a mathematical nightmare of fuel calculations versus combat time over target. Every long-range patrol ended with pilots gliding back to base on fumes, praying their engines wouldn't quit before the runway appeared beneath their wings. The technique that would double American combat range had been discovered by accident 3 weeks earlier when Lieutenant Robert Hayes, a former crop duster from Nebraska, forgot to adjust his mixture controls during a training flight over the Mojave Desert. Instead of the rich fuel mixture that flight manuals prescribed for maximum power, Hayes had inadvertently run his engine at settings so lean that any reasonable pilot would have expected catastrophic failure. But his Mustang had flown for 6 hours straight, covering twice the distance that identical aircraft achieved using standard procedures. Hayes landed at Hamilton Field with fuel gauges reading nearly empty but engine temperatures within normal parameters. His mechanic, Sergeant Tony Castellano, a former Chevrolet factory worker from Detroit, had initially assumed the fuel flow indicators were malfunctioning. 20 years of automotive experience had taught him that engines required rich fuel mixtures for reliable operation. Lean settings meant detonation, overheating, and mechanical failure that would leave pilots walking home from enemy territory. But Hayes' engine showed no signs of distress despite operating conditions that violated every principle of aircraft power plant management. The cylinders ran clean, temperatures remained stable, and power output stayed within acceptable limits throughout the entire flight. The mathematical impossibility of the situation gnawed at Castellano's mechanical instincts like a puzzle missing crucial pieces. The telephone call that would change everything came 2 days later from Wright-Patterson Army Air Base in Ohio. Colonel William Turner, chief of the Army Air Force's Technical Development Division, had been reviewing fuel consumption reports from Pacific theater operations with growing concern about American tactical limitations imposed by range constraints. Every major bombing mission required fighter escorts that consumed fuel so rapidly they could barely reach enemy territory before turning back to avoid running dry over hostile waters. Japanese fighters, meanwhile, seemed to operate with unlimited range, appearing over Allied bases hundreds of miles from any known enemy airfield. Intelligence reports suggested that enemy pilots possessed some technical advantage that allowed extended operations far beyond American aircraft capabilities. The strategic implications were devastating for Allied bombing campaigns that required fighter protection throughout increasingly long missions against targets deep in Japanese-controlled territory. Turner had heard rumors about experimental fuel mixture techniques being tested in California. Pilots whispered about lean engine operations that defied conventional wisdom while dramatically extending aircraft range. But official Army Air Force's technical manuals strictly prohibited such procedures, classifying them as dangerous modifications that would destroy engines and kill pilots who attempted them under combat conditions. The resistance from established aviation experts flowed like doctrine through every level of military hierarchy. At Wright Field, engine specialists argued that lean fuel mixtures would cause detonation that would crack cylinder heads and destroy pistons within minutes of takeoff. The National Advisory Committee for Aeronautics had published technical papers proving that aircraft engines required rich mixtures for reliable high-altitude operation, where air density decreased and combustion became increasingly difficult to sustain. Even Charles Lindbergh, aviation's most respected voice, had questioned lean mixture techniques during a classified briefing at the Pentagon 6 months earlier. His transatlantic flight experience provided credibility that few pilots could challenge, and his concerns about engine reliability carried weight throughout the Army Air Force's command structure. But fuel consumption statistics from combat operations painted an increasingly desperate picture of American tactical limitations. B-17. Flying fortresses required fighter escorts that could barely reach German industrial targets before fuel constraints forced them to abandon the bombers they were supposed to protect. P-38. Lightning fighters operating from Henderson Field could patrol for only 90 minutes before returning to base, leaving gaps in coverage that Japanese bombers exploited with devastating effectiveness. The breakthrough came when Major Charles Lindbergh himself arrived at Hamilton Field on March 15, 1943, carrying orders to personally evaluate the lean mixture techniques that had generated such controversy within Army Air Force's technical circles. His presence transformed what had been informal experimentation into official evaluation that would determine whether American pilots would gain access to procedures that could double their combat effectiveness. Lindbergh climbed into the cockpit of Mitchell's P-51 Mustang with the methodical precision that had made him aviation's most celebrated pilot. 2 decades of flying experience had taught him to approach every aircraft with systematic attention to detail that left nothing to chance. But even his legendary skill could not have prepared him for what he would discover during the next 4 hours of flight testing over California's desert landscape. The engine started normally, its Packard Merlin power plant settling into the familiar rhythm that had powered British Spitfires over England and American fighters across the Pacific. Standard takeoff procedures called for full, rich mixture settings that provided maximum power for departure while ensuring adequate cooling during the critical phases of flight when engine failure would prove immediately fatal. But once airborne and climbing toward cruising altitude, Lindbergh began the systematic process of leaning the fuel mixture far beyond anything recommended in official technical manuals. The procedure required delicate touch and constant monitoring of engine parameters that could shift from normal operation to catastrophic failure within seconds of careless adjustment. Fuel flow decreased dramatically as Lindbergh found the precise mixture setting that provided adequate combustion while eliminating the excess fuel that standard procedures wasted through incomplete burning. Engine temperatures remained stable despite mixture settings that conventional wisdom insisted would cause immediate overheating and mechanical destruction. The fuel consumption measurements that emerged from Lindbergh's test flight challenged everything the Army Air Forces believed about aircraft engine operation, where standard rich mixture procedures consumed fuel at rates that limited combat missions to 3 hours maximum. Lean operations extended flight time to nearly 6 hours with identical fuel loads. The range improvement was mathematically undeniable and tactically revolutionary. 200 miles from Hamilton Field, flying at settings that should have destroyed his engine, Lindbergh's Mustang continued operating with mechanical reliability that defied expert predictions. The fuel gauges showed consumption rates 40% lower than standard procedures while maintaining cruise speeds and power output sufficient for combat operations. The implications for American strategic bombing campaigns were staggering beyond anything military planners had dared imagine. As Lindbergh guided the Mustang back toward Hamilton Field, he understood that he had discovered more than just an engine technique. He had found the key that would unlock American air power from the fuel consumption constraints that had limited every major bombing mission since the war began. The mathematical proof was irrefutable, documented by instruments that recorded every parameter of an engine operation that redefined what American pilots could accomplish with existing aircraft. The radio crackled to life as Lindbergh descended through 8,000 feet, his voice carrying the measured tone of a pilot who had just witnessed something that would rewrite the tactical playbook for every American fighter squadron in the Pacific. Hamilton Field, this is Experimental Flight 779er. Request priority landing for immediate debrief with Colonel Turner. Below him, the California desert stretched endlessly toward the horizon, the same barren landscape that had witnessed countless training flights where pilots learned to conserve fuel like precious water in a desert. But the gauges in Lindbergh's cockpit told a different story. After 4 hours of flight operations that should have consumed 3/4 of his fuel load, the tank still registered half full with enough gasoline remaining for another 2 hours of combat patrol. The landing gear touched concrete with the familiar screech of rubber against asphalt as ground crews rushed toward the aircraft that had just completed what military aviation experts had declared impossible. Sergeant Castellano waited beside the fuel truck, his Detroit-trained instincts preparing for the worst while hoping for mechanical vindication of procedures that challenged everything he had learned about internal combustion engines. Colonel Turner emerged from the operations building with the brisk stride of a man whose career depended on separating aviation fact from wishful thinking. 25 years of military service had taught him to approach revolutionary claims with methodical skepticism that demanded proof rather than promises. Too many miracle solutions had emerged from experimental programs only to fail catastrophically under combat conditions, where mechanical reliability meant the difference between mission success and pilot obituaries. Lindbergh climbed down from the cockpit with deliberate movements that reflected both physical fatigue and mental processing of what he had experienced during 4 hours of flight operations that violated every principle of aircraft engine management. His leather flight jacket showed the sweat stains of concentrated flying, but his expression carried the quiet satisfaction of a pilot who had pushed boundaries and discovered new possibilities rather than mechanical failure. The fuel measurement process began immediately as Castellano connected his calibrated equipment to the Mustang's fuel system, documenting exactly how much gasoline remained after operations that standard procedures would have required 50% more fuel to accomplish. The mathematics were becoming undeniable with each gallon that flowed into the measuring tank, proving that lean mixture techniques could extend American fighter range far beyond anything Japanese intelligence had calculated into their defensive strategies. 42% fuel remaining after 4 hours 15 minutes of flight operations, Castellano announced, his voice carrying the professional amazement of a mechanic who had just witnessed internal combustion engineering principles being rewritten by practical application. Standard rich mixture procedures would have required refueling after 2 hours 40 minutes maximum. Turner made careful notes in his logbook, understanding that these measurements would travel to Pentagon briefing rooms where strategic bombing campaigns were planned around fuel consumption limitations that might no longer apply to American fighter operations. Every additional hour of combat patrol time translated directly into tactical advantages that could protect bomber formations throughout their entire missions, rather than abandoning them at the most dangerous phases of penetration into enemy territory. The engine inspection revealed the mechanical reality behind fuel consumption improvements that seemed too good to survive contact with combat conditions. Lindbergh's Packard Merlin showed no signs of the detonation damage that experts had predicted would destroy any power plant operated at lean mixture settings for extended periods. Cylinder head temperatures had remained within normal parameters, despite fuel mixture adjustments that conventional wisdom insisted would cause immediate overheating and catastrophic mechanical failure. Combustion chamber examination showed clean burning characteristics that indicated complete fuel consumption, rather than the rich mixture waste that standard procedures accepted as necessary for engine protection. The lean settings had eliminated unburned fuel that normally passed through the combustion process without contributing to power output, creating efficiency improvements that translated directly into extended range capabilities. But the real test would come under combat conditions where enemy fighters would challenge American pilots to extract maximum performance from their aircraft, while managing fuel consumption over distances that determined whether bomber crews returned home or became statistics in Japanese victory reports. Laboratory measurements meant nothing if lean mixture techniques failed when pilots needed them most desperately. The telephone rang in Turner's office at 0600 the following morning, connecting him to Admiral Chester Nimitz's headquarters in Pearl Harbor, where Pacific Fleet operations were being planned around fighter escort limitations that constrained every major bombing mission against Japanese industrial targets. The voice on the other end belonged to Captain Harold Morrison, Air Operations Officer, whose responsibility included matching American tactical capabilities against Japanese defensive strategies that seemed to anticipate exactly how far American fighters could penetrate before fuel constraints forced them to withdraw. "We're losing bombers because our escorts can't stay with them deep into enemy territory," Morrison explained, his words carrying the weight of operational reality that transcended theoretical discussions about aircraft performance. "Japanese fighters attack our formations when they know American escorts have turned back. We need longer range, or we're going to lose this air war through attrition that favours defenders operating close to their bases." Turner understood the strategic implications better than most Pentagon staff officers who analysed Pacific operations from Washington conference rooms rather than combat airfields where fuel consumption determined tactical success or failure. Every B-25 medium bomber mission against Japanese shipping required fighter protection that could barely reach target areas before fuel limitations forced escorts to abandon the aircraft they were supposed to protect throughout the most dangerous phases of bombing operations. The experimental program expanded rapidly as word of Lindbergh's successful test flights spread through Army Air Force's technical channels like Aviation Gospel that promised solutions to range problems that had constrained American offensive operations since Pearl Harbor. Within 72 hours, Hamilton Field had received orders to train squadron commanders from every fighter group preparing for Pacific deployment in lean mixture techniques that could transform their tactical capabilities. Captain Robert Scott arrived from the China-Burma-India theatre, carrying combat experience that provided context for fuel consumption improvements that seemed almost too significant to believe. His P-40 Warhawk squadrons had been fighting Japanese fighters over Burma with aircraft that possessed barely enough range to reach combat areas before fuel constraints forced immediate return to base, leaving American bomber formations vulnerable to enemy interceptors that seemed to operate with unlimited endurance. The training program that emerged from Hamilton Field would eventually revolutionize American fighter tactics across every theater of operations. But first it had to overcome decades of aviation engineering doctrine that insisted rich fuel mixtures were essential for reliable high-altitude combat operations. Every pilot arriving for lean mixture training brought skepticism, learned from flight instructors who had taught them that fuel conservation meant engine destruction under the stress conditions that characterized aerial combat. Flight Lieutenant David Park, a Royal Air Force exchange pilot with Battle of Britain experience, represented the international implications of American fuel consumption breakthroughs that could affect Allied air operations across multiple theatres, where range limitations had constrained offensive bombing campaigns against Axis industrial targets. His Spitfire experience over England had taught him that fuel management often determined whether fighter pilots could complete their missions or abort due to insufficient gasoline reserves for safe return to base. The resistance from established military aviation experts grew more vocal as Hamilton Field's experimental program produced results that challenged fundamental assumptions about aircraft engine operation under combat conditions. At Wright-Patterson Air Base, propulsion engineers argued that lean mixture techniques represented dangerous shortcuts that would cost American lives when engines failed over enemy territory, where mechanical reliability meant survival rather than statistical analysis. Dr. Marcus Webb, chief propulsion engineer at Wright-Patterson, published technical bulletins warning that lean mixture operations would cause cylinder head cracking within 50 hours of combat use. His mathematical models, based on 2 decades of engine development experience, predicted catastrophic failures that would strand American pilots in Japanese-controlled territory when their power plants succumbed to thermal stress and mechanical breakdown under conditions where rescue was impossible. The controversy reached the highest levels of military command when General Henry Arnold, commanding general of the Army Air Forces, demanded comprehensive evaluation of techniques that promised tactical advantages, while potentially sacrificing pilot safety through experimental procedures that violated established engineering principles. Arnold's position was brutally pragmatic. American industrial capacity could replace aircraft faster than trained pilots, making any technique that increased pilot casualties strategically counterproductive, regardless of theoretical performance improvements. The evaluation committee that assembled at Hamilton Field in April 1943 represented every aspect of American military aviation, from combat operations to engineering development. Colonel Francis Gabreski brought fighter experience from European theatre operations where fuel limitations had forced American escorts to abandon bomber formations during the most critical phases of penetration into German-controlled airspace. His P-47 Thunderbolt squadrons had watched helplessly as Luftwaffe interceptors attacked Allied bombers after American fighters reached their fuel consumption limits and turned back toward England. Major Thomas Maguire arrived from 5th Air Force operations in New Guinea, carrying combat statistics that revealed the deadly mathematics of fuel consumption versus tactical effectiveness. His P-38 Lightning squadrons faced Japanese fighters that seemed capable of extended combat operations, while American aircraft were forced to withdraw due to fuel constraints that left bomber formations vulnerable during precisely the moments when fighter protection was most desperately needed. The systematic testing program that emerged would subject lean mixture techniques to conditions that exceeded anything pilots would encounter during actual combat operations. Every parameter would be measured, documented, and analysed by engineers who understood that mathematical precision was the only acceptable foundation for procedures that would determine whether American airmen lived or died over enemy territory. Sergeant William Rodriguez, a former Packard automotive engineer who had transitioned to aircraft power plant maintenance, supervised the engine monitoring equipment that would document exactly how lean mixture operations affected mechanical reliability under stress conditions. His Detroit industrial background provided perspective on internal combustion engineering that transcended aviation-specific applications, understanding that fundamental thermodynamic principles governed engine operation regardless of whether power plants propelled automobiles or fighter aircraft. The test aircraft, a North American P-51D Mustang designated for experimental operations, received instrumentation that monitored every aspect of engine performance from cylinder head temperatures to combustion chamber pressures. Sensors measured parameters that normal combat aircraft never recorded, creating comprehensive documentation of how lean fuel mixtures affected power plant operation under conditions that simulated extended combat patrol over enemy territory. Captain Mitchell strapped himself into the cockpit on April 18, 1943, carrying responsibility for proving whether techniques that promised doubled combat range could survive the mechanical stress of actual implementation. His test card specified fuel mixture settings that conventional wisdom insisted would destroy his engine within minutes of takeoff, but mathematical analysis suggested could extend his aircraft's operational radius from 300 miles to nearly 600 miles with identical fuel loads. The engine started normally, its familiar Packard Merlin note settling into rhythms that had powered countless training flights over California's desert landscape. But today's mission would push boundaries that separated theoretical possibility from mechanical reality, testing whether American pilots could gain tactical advantages through procedures that challenged every principle of aircraft power plant management they had learned during flight training. Takeoff proceeded with standard rich mixture settings that provided maximum power for departure, while ensuring adequate cooling during the critical phases where engine failure would prove immediately fatal. The Mustang lifted off Hamilton Field's concrete runway with authority that spoke of Detroit engineering adapted for military aviation, climbing steadily toward test altitudes where lean mixture evaluation would begin under conditions that simulated extended combat patrol over Japanese-controlled territory. At 8,000 feet, Mitchell began the systematic process of adjusting fuel mixture controls far beyond anything recommended in official technical manuals. The procedure required constant attention to engine parameters that could shift from normal operation to catastrophic failure within seconds of improper adjustment, demanding pilot skills that transcended routine flight operations into experimental test flying, where mechanical limits were discovered through direct experience rather than theoretical analysis. Fuel flow gauges registered dramatic decreases as mixture settings approached the lean limits where combustion became increasingly difficult to sustain. Engine temperatures fluctuated as the power plant adapted to fuel delivery rates that provided barely adequate combustion while eliminating the excess gasoline that rich mixture procedures wasted through incomplete burning. Every instrument reading challenged conventional understanding of how aircraft engines should operate under conditions where reliability was paramount. The radio crackled with updates to Hamilton Field's control tower as Mitchell reported engine parameters that defied expert predictions about lean mixture operations. Cylinder head temperatures remained within normal limits despite fuel settings that should have caused immediate overheating. Oil pressure stayed constant, while power output maintained levels sufficient for combat operations against enemy fighters that would challenge every aspect of aircraft performance. 150 miles from Hamilton Field, flying deeper into California's desert than any previous test flight had attempted, Mitchell's Mustang continued operating with mechanical reliability that challenged fundamental assumptions about aircraft engine management. The fuel gauges showed consumption rates that would allow patrol operations extending far beyond anything Japanese defensive planners had calculated into their interceptor deployment strategies. Ground control radar tracked the experimental flight as it approached 200 miles from base, distances that represented the outer limits of fighter escort capability using standard fuel consumption procedures. But Mitchell's engine continued running smoothly on mixture settings that conventional wisdom insisted would have caused mechanical failure long before reaching such extended ranges from base operations. The implications for Pacific theater bombing campaigns became increasingly apparent as flight time extended beyond 3 hours, with fuel gauges still registering sufficient gasoline for another 2 hours of operations. American bomber formations could receive fighter escort protection throughout their entire missions, rather than facing the most dangerous penetration phases without adequate air cover due to fuel consumption limitations that had constrained every major offensive operation since Pearl Harbor. At the 3-hour 30-minute mark, Mitchell began the return flight toward Hamilton Field with fuel reserves that standard procedures would have exhausted after 2 hours 15 minutes of identical operations. The mathematical proof was becoming undeniable through direct measurement of consumption rates that challenged every assumption about aircraft power plant efficiency under extended combat conditions. The engine inspection that followed Mitchell's landing revealed mechanical evidence that supported fuel consumption improvements, which seemed too significant to survive contact with engineering reality. His Packard Merlin showed no signs of the thermal stress damage that experts had predicted would result from lean mixture operations extended beyond safe operational limits. Combustion chambers remained clean while cylinder heads displayed none of the cracking that mathematical models had forecast as inevitable consequences of experimental fuel management techniques. Dr. Webb arrived from Wright-Patterson the following morning carrying skepticism that demanded comprehensive mechanical analysis before accepting results that contradicted established propulsion engineering principles. His examination of Mitchell's engine components revealed combustion characteristics that indicated complete fuel utilization rather than the wasteful burning that rich mixture procedures accepted as necessary for power plant protection under combat stress conditions. The breakthrough had implications extending far beyond individual aircraft performance into strategic capabilities that could transform American bombing campaigns across every theater of operations. Fighters equipped with lean mixture techniques could escort bomber formations throughout their entire missions, rather than abandoning them during the penetration phases where enemy interceptors concentrated their attacks against Allied aircraft operating without adequate fighter protection. But the real test would come when combat pilots attempted these procedures under conditions where Japanese fighters challenged every aspect of American aircraft performance, while fuel management determined whether missions succeeded or failed through tactical limitations imposed by consumption rates that had constrained offensive operations since the war began. The classified telegram reached General Curtis LeMay's headquarters on Guam at 0430 hours on May 3, 1943. The message contained 5 words that would reshape American strategic bombing doctrine across the Pacific theater. Hamilton Field lean mixture approved for combat implementation. LeMay, commander of the 21st Bomber Command, understood immediately that these words represented more than technical authorization. They meant his B-29 superfortresses could finally reach targets in the Japanese home islands with fighter escort protection throughout the entire mission profile. For 18 months, American bomber crews had faced an impossible tactical equation. Japanese industrial targets lay beyond the effective range of escorted operations, forcing commanders to choose between sending unprotected formations against heavily defended objectives or limiting attacks to secondary targets within fighter escort radius. The mathematics of fuel consumption had determined strategic priorities more than enemy defensive capabilities or target importance. Lieutenant Colonel Paul Tibbets received his orders 3 days later at Wendover Army Air Base in Utah, where his 509th Composite Group was preparing for operations that would require unprecedented precision flying over distances that stretched conventional aircraft capabilities to their absolute limits. The mission profiles his crews practiced demanded fuel management techniques that could extend B-29 range by 40%, while maintaining formation integrity throughout flight durations exceeding 12 hours. The training program that emerged at Wendover challenged everything American pilots had learned about power plant management during conventional flight instruction. Staff Sergeant Anthony Ricci, a former Pratt & Whitney factory mechanic from East Hartford, supervised engine modifications that would allow the massive Wright R3350 Cyclone power plants to operate reliably on mixture settings that standard procedures classified as dangerous beyond acceptable risk parameters. Each B-29 carried 4 engines producing 2,200 horsepower per power plant, consuming fuel at rates that limited strategic missions to targets within 800 miles of base operations. But lean mixture techniques promised to extend that radius to nearly 1,200 miles, bringing every major Japanese industrial center within range of American bombing operations launched from newly constructed airfields in the Mariana Islands. The resistance from Wright-Patterson intensified as reports of successful lean mixture operations spread through Army Air Force's technical channels. Dr. Webb published urgent bulletins warning that extended lean operations would cause catastrophic engine failures during the precise moments when mechanical reliability was most critical for mission success and crew survival over enemy territory where rescue was impossible. His mathematical models predicted thermal stress failures within 6 hours of lean mixture operations under combat loading conditions. The Wright R3350 engines powering B-29 formations represented the most complex aircraft power plants ever produced, incorporating supercharging systems and cooling technologies that pushed engineering boundaries beyond anything attempted in previous aviation applications. Experimental fuel management techniques on such sophisticated power plants seemed like mechanical suicide disguised as tactical innovation. But combat statistics from Pacific operations painted an increasingly desperate picture of American strategic limitations imposed by fuel consumption constraints. Major Robert Morgan, pilot of the Memphis Belle during European operations, had transferred to Pacific Theater B-29 squadrons carrying experience that revealed how fuel management determined bombing effectiveness more than defensive fighter opposition or anti-aircraft artillery concentrations. Every mission against Japanese steel production facilities required fuel calculations that forced tactical compromises between target selection and aircraft recovery. Crews faced the brutal choice between carrying maximum bomb loads that limited range or reducing ordnance to ensure sufficient fuel reserves for safe return to base operations. The strategic bombing campaign that was supposed to cripple Japanese war production had become a series of mathematical exercises in fuel consumption optimization. The solution lay in procedures that aviation experts continued to insist would destroy engines and kill crews through mechanical failures that occurred at precisely the worst possible moments during combat operations. But the evidence from Hamilton field testing was becoming mathematically undeniable, despite expert predictions of catastrophic power plant failures under extended lean mixture operations. Captain Charles Sweeney arrived at Wendover carrying B-29 combat experience from missions over Japanese industrial targets that had tested every aspect of aircraft and crew endurance. His boxcar had flown formation missions lasting 11 hours while maintaining fuel reserves that barely permitted safe recovery to base operations. The margin between mission success and fuel exhaustion had become so narrow that weather delays or navigation errors could transform routine bombing operations into emergency fuel conservation exercises. The training flights that began at Wendover in June 1943 would determine whether American strategic bombing could achieve the sustained operations necessary to cripple Japanese industrial capacity before invasion became the only alternative to prolonged Pacific warfare. Each test mission pushed fuel consumption boundaries further beyond conventional limits, while documenting engine performance under conditions that simulated extended combat operations over enemy territory. Flight Engineer Technical Sergeant James Korkowski monitored power plant parameters during flights that challenged every assumption about aircraft engine reliability under sustained lean mixture operations. His background with Wright Aeronautical Corporation provided technical perspective on R3350 engine capabilities that transcended pilot training focused on operational procedures rather than mechanical engineering principles governing internal combustion power plant design. The engines performed with reliability that defied expert predictions about thermal stress failures and mechanical breakdowns under fuel mixture settings that conventional wisdom classified as destructive to power plant longevity. Cylinder head temperatures remained within acceptable parameters, while oil consumption stayed constant, despite operating conditions that should have caused immediate lubrication system failures and catastrophic mechanical damage. By August 1945, LEN mixture techniques had transformed American air power from a fuel-constrained force into the longest-range striking capability in aviation history. The procedures that aviation experts had dismissed as mechanically impossible enabled B-29 formations to reach targets throughout the Japanese home islands while maintaining fighter escort protection that made strategic bombing campaigns devastatingly effective. What began as an accidental discovery by a crop duster from Nebraska had become the tactical advantage that helped end the Pacific War through sustained operations that Japanese defensive planners had calculated beyond American capabilities.